Hello and welcome to today's tutorial focusing on vectors and 2D and 3D kinematics. This is quiz 2 of the Honors Physics 271 Fall 2014 class in Physics, Classical Mechanics. And today we're going to walk through the quiz number 2 solutions, which is fairly simple, but there's some challenging notions in here and that we'll cover them today. So let's start off with just reading the problem presented, and I've put the problem up here, and I've put the figure that we're basing this problem off in the corner for ease of access. So let's read the problem. So it says you are playing soccer, and you are the goalkeeper, and you're at the origin 0, 0, 0, and the field is in the XY plane as shown in Figure 1. So you want to shoot the ball with a velocity vector v naught, defined by v naught and each Cartesian coordinate, so that it reaches the midfield at player r, which is given by a distance, and the exact time the player gets there. The ball travels through the air in one projectile motion, and the player is running with a velocity of 4 meters per second towards r from a point r naught. So before we begin, let's just define, for our ease, the coordinates of this point r naught, and we'll define these distances relative to each other. So we know that r is a point of 96 in the x direction, and r naught is 66, so we can define this player, this other player, we can define him relative to us by simply subtracting. So what we do is we get an x displacement of 30 meters, and then in the y we have 40 meters. Okay, so now let's look at part A. So part A asks, find the distance, the magnitude of vector r minus vector r naught. So first let's start off by defining the vectors. So r is equal to 96 in the x plus 40 in the y and nothing in the z. And then r naught is equal to, r naught is equal to 66 x plus 0y. Oops, sorry, that 0 was bad. Plus 0 y, and then also 0 z. Ooh, and I forgot to put a hat on that. Okay, so now we need to find the magnitude of r minus r naught. So let's first calculate r minus r naught. And this is simply vector subtraction, which is equal to 30 x hat plus 40 y hat, and then there's no z component here. Alright, oops, I don't know why I did that, sorry. There's z. And now we simply need to calculate this magnitude, which is simply, and I'll call this, for ease, I'll call this new vector ri. So this vector ri, I'm sorry, this is, oops, let's get rid of this. This is not a vector, it's a scalar product. So I'll just write it as the magnitude of r minus r naught is given by the square root of this square root of the magnitude, so it's each component squared plus 40 squared, and we can ignore the 0 because that yields nothing, and we get 50 meters. Excuse me, 50 meters. So now we have that, okay? So now, okay, now let's do part B. Okay, so part B asks how long does it take for the player to get from R0 to R. Okay, so we know that the player is running, the player has to run 50 meters, and he's doing so with a constant velocity, CV, of 4 meters per second. So now, because of this, we can simply do dimension analysis to find the time it takes. So we can simply say that the final time is equal to the distance needed to travel, 50 meters, divided by 4 meters per second. The meters cancel, and we are simply left with 25 over 2 seconds. Alright, so now let's move on to part C. And many of you may think this is simple, doing these vector problems, but there are this problem is going to get a little complex later on, and it can never hurt to practice. So let's do part C. So it says on the figure, draw the velocity vector. So that velocity vector of the ball is simply given by the point from U to the point of the meetup with the other players. So we can draw this vector like so. Okay, and we can actually just label that. We can label that V0 x, V0 y, and then 0 for the z component. Okay, cool. So now for C, the second part is asking what is V0 y divided by V0 x, and it also wants us to describe the ball's motion on the x plane, ignoring the z direction. So to describe the motion of the ball, it simply revolves around the fact that the acceleration is 0. So because of this, the ball goes in a straight line, and that straight line is parallel to r. So we can say that because a is 0, the ball goes in a straight line, which is parallel to r. Okay. So now it also wants V0 y over V0 x. So what this simply is the it's simply the r y component divided by the rx component, and I'll show you that decomposition in a second. It's so we need to find V0 y over V0 x, which is simply equal to the ry component divided by the rx component, which in this case is equal to what you can find right here, 40 meters divided by 96 meters, which is equal to about 5 over 12 meters. I'm sorry, not over 12 meters, just 5 over 12. Okay, so now let's do part D. So part D asks, what is the distance of r, the magnitude of r? So this is fairly simple. The magnitude of vector r is simply the square root of the component squared. So we take the square root of 96 squared plus 40 squared, and there's no z component, so we can ignore that. And that yields, in the end, decomposition yields approximately, what is that? That's 8 times 13, or 104 meters precisely. Okay, perfect. So now let's do part E. Alright, and now part E is asking us to find V naught x and V naught y. So we're given this time constraint, which we found above, which is 25 over 2 seconds. So what we know is that at 25 over 2 seconds, the ball must reach R. So what we can do is we can evaluate the equations relative to the velocity equations. So what we can define is what we'll do is we'll define z of b of t final, and we'll set that equal to v naught x of tf, and that is equal to 96 meters. Or what we can do is we can write this as v naught x is equal to 192 over 25 meters per second, and then v naught y is simply equal to 5 over 12, which we found above, times 192 over 25, or 16 over 5 meters per second. Alright, great. So now we can solve part F. Part F asks us to explain the ball's motion in the z direction and then find v naught of z. So because this is projectile, we know that A of z is simply the negative gravitational force. So we can denote AZ as constantly negative g, constant g, I'm sorry, that's a constant A. Okay, and so now what we can simply do is write this to find v naught z component. We can simply write it using a kinematic equation. So we can say z of t is equal to 0 plus v naught z times time minus 1/2 g of t squared, a simple kinematic equation. And so what we do know is we know that z of tf is equal to 0, and thus v naught of z, using standard algebra, is equal to 1/2 g times 25 over 2, and that yields 125 over 2 meters per second for the velocity of the z component. Alright, great. So now let me just make some extra room down here for the last and final part, which is part G. And so I'll actually what I'll do is let me just quickly move this up. Let me move this up. I'll move this up here so that we can have some room to do part F down below. Alright. Oops. Apologize for that. Alright. So now this is part G. Okay. So part G is asked, what is the initial angle theta naught of this projectile motion? So what we can do to find this is just draw out the coordinate axes. It's a simple problem. So we can just draw out this coordinate system, and we can denote the resultant projectile like so, like any other classic projectile problem. Okay, and so there's your y and x component. So this is v naught of z right there. Here's our angle that we desire to find, theta naught. And down here, this component, we can denote it as the square root of v naught x squared plus v naught y squared. Alright, so using that, and we could just, all we have to do is use trigonometry. We can denote this as, well, I prefer to use tangent here. We can say that tangent of theta naught is equal to, tangent is opposite over adjacent, so it's v naught z divided by the square root of v naught x squared plus v naught y squared. And what that yields is, plugging in the values from what we found up above, it's 125 over 2 divided by 208 over 25, which is simply equal to sorry, let me just do the calculation. This is simply equal to, is equal to about 7.5, and then plugging that in, we can use tangent inverse. What we get is a theta angle of about 80 degrees. And there you have it. There is all the solutions for quiz number 2, explained and kind of elaborated on. And I hope you enjoyed this tutorial, and good luck in your physics education, and check back later for tutorial 3. Thanks.